Welcome back. You probably heard about heat pumps. To be able to design heating and cooling systems with heat pumps, you need to know their basic working principles and energy flows. So today we will dive into the magic of heat pumps to learn if it is actually magic. Let's find out. The objectives of this lecture are for you to learn what a heat pump and its basic working principle is, how the energy flows of a heat pump are quantified, and what the efficiency of a heat pump is. A heat pump is a device that transforms heat from a low temperature source to a higher temperature sink. This is exactly opposite of the natural flow of heat. Therefore, mechanical work is needed to make the heat flow from cold to warm. Let's first talk about the energy flows and consider the heat pump to be a black box for now. The figure shows that the amount of thermal energy, Q in, is needed as input for the heat pump. This is thermal energy usually removed from a low temperature source of heat. For example, outside air, the subsurface or surface water. Because the heat pump extracts heat, the used source of heat cools down. Please note that this feature is used in refrigerators and air conditioning units, such as cooling devices. They use exactly the same working principle as heat pumps. For cooling, we are interested in the cooling generated and dump the heat quite often into the outside air. Now back to heat pumps, as we are now interested in the generated heat. Due to adding work, the heat pump increases the temperature of the extracted heat. And because of the conservation of energy, also heat generated by the work is added to the Q out as well. As the equation shows, the amount of heat added corresponds to the amount of work done. Most heat pumps use electricity to run a compressor to do the work. Because the low temperature heat we get from the environment, Q in, is free, the efficiency of a heat pump is usually calculated by only taking into account the amount of primary energy used to do the work. The efficiency of a heat pump is referred to as the coefficient of performance, COP, and is defined as the ratio between the delivered energy over the electricity used. As a result, heat pump COPs usually have values of over 4 and sometimes even higher than 7. So you get 4 times as much of heat for each unit of primary energy you put in. That is quite different with common electrical or gas-fired boilers, where you get 90 to 100% conversion to thermal energy. Now, time to find out how the heat pump does this magic. The most popular and basic thermodynamic cycle for heating and cooling is the so-called vapor compressor refrigeration cycle, which is also used in air conditioning units and refrigerators, as I mentioned before. In such cycle, a working medium or refrigerant is undergoing compression and expansion, and in between the working medium is condensing and evaporating due to heat exchange. Let us look in detail at this cycle, which in this schematic runs in the clockwise direction. We will step by step discuss the occurring processes at each of the 4 main components of the heat pump, which are the compressor, the condenser, the expansion valve, and the evaporator. The temperature levels used in this example represent common values for heat pump used in space heating, but vary between heat pumps depending on their purpose and design. Let's start at the evaporator. The cold working medium enters the evaporator from the bottom. The temperature is such that it allows to absorb the thermal energy from the external source we are using, in this case the environment. At the occurring temperature and pressure, the working medium of the heat pump will evaporate and leave the evaporator as a gas, 10 to 20 degrees warmer than the fluid which entered the evaporator. This gas is then compressed by the compressor, causing the increase in temperature because the molecules are closer together, resulting in more friction and collisions which create heat. This is the part of the heat pump where the mechanical work is done and where the energy from the work is added to the working medium as well. Then, this high pressure warm gas is fed into the condenser from the top. Here the heat is exchanged with the sink of thermal energy. In case of space heating, this is often an underfloor heating system, typically running at supply and return temperatures indicated on the slide. At these pressure and temperature conditions, the working medium condenses. So at the bottom of the condenser, the working medium is still at high pressure as no pressure losses occur in the condenser. But now again a fluid, 10 to 20 degrees colder than the gas which entered the condenser. The last step in the cycle is the working medium passing the expansion valve, where pressure is released. This will cause the opposite of compression, decrease of temperature, and usually also partly evaporation. So a cold fluid-gas mixture will enter the evaporator again, which will fully evaporate by taking up heat from the external source of heat. Heat pump manufacturers design the composition of the working medium such that it evaporates and condenses at specific pressures and temperature levels corresponding to the required application of the heat pump. As we use environmental sources of heat as input, the available temperature may vary. Also, the heat demand in buildings or other heating processes vary. As a result, the temperature conditions both at the evaporator and the condenser varies over time. Therefore, you need to be aware that the momentary occurring COPs will vary, and assessing heat pump performance requires the integration of occurring COPs over time to calculate the average COP. Both the condenser and evaporator can be water to working medium heat exchangers as described here, but one of the two or both can also be a radiator with a fan transferring the heat from or to the air, as is also the case for air conditioning units. Depending on the type of application, we can have air-to-air heat pumps, air-to-water, water-to-air, or water-to-water heat pumps. As exchange with air is less efficient and requires additional energy used for the fans, such heat pumps usually have a lower efficiency. To summarize our learnings, we have learned that heat pumps transform thermal energy from low temperature to high temperature. Because this is in the opposite direction of the normal flow of heat, this requires mechanical work. The vapor expansion compression cycle consists of 4 key components to run the cycle. The performance of a heat pump is usually described by the COP, which is the ratio of the heating output over the primary energy input to run the machine. Thank you for your attention. A lot of additional detailed information on heat pumps and refrigeration systems can be found in textbooks and websites online.